IITP in Japan. And first, I thank the organizer. I would like to thank the organizer for inviting me to this wonderful workshop. And okay, I will talk about bulk reconstruction in ADCFT. And this talk is based on these papers. Okay. First, then the bulk reconstruction in the CFT is very important. Actually, bulk reconstruction means it's what ADCFT, how ADCFT works. So it's the heart of the ADCFT. So, and especially if we can understand this bulk reconstruction, we can also explain how the bulk gravity theory emerges from CFT. Okay. So bulk reconstruction means how to reconstruct the bulk state or operator from the CFT. Okay. And of course, there is a well-known formula, HKLL reconstruction formula, or a free theory on ADS. And free theory on ADS means equivalent to strong coupling limit of large N CFT. Okay. So this formula is integration of CFT field over some region. Some region means these region here. So, and this formula is not so simple and rather counterintuitive with causality, I think. Okay. And in this talk, I will show that bulk reconstruction is rather simple and has an intuitive picture using an alternative reconstruction formula, of course, which is equivalent to the HKL formula, but alternative reconstruction formula I will show. And for example, bulk local set at the center here is given by a time evolution of uniformly distributed CFT primary state. Here, uniformly means this S1 represents a whole CFT space, and this is the time. So CFT primary operator integrating over this one gives exactly this bulk locus. So here only right-track trajectories appear here. So it's simple. Anyway, I will talk about this picture. Okay, so this is I think very interesting. And first, I will talk about the low energy spectrum of CFT and its relation to the bulk reconstruction in ADCFT. And user formulation of the HFT is using a GKP bit emulation. It's for the Patchon function. The boundary condition ADS is identified as source time in CFT. So it's with the source time. So it's the equivalence of correlates. Right? But there is another formulation of ADS-CFT. It's usually used in ADS-QCD or something like that. It's in operator formalism. There's no sources. Just just a state and time evolution, something like that, or spectrum. So in this formalism, equivalence between ADS-CFT duality means equivalence between the Hilbert space and Hamiltonians of gravity on ADS and CFT. Okay. So here CFT means I mean, in this talk I want to consider the global ADS. So CFT is on the time times sphere. Okay. And what we can determine explicitly for the low energy spectrum of CFT is which is realized as a large strong coupling theory. I mean, we can determine low energy spectrum of CFT explicitly for the large strong coupling gauge theory. It means leading order in large limit, but not assuming supersymmetry, not assuming strength, deep brain, not assuming dual gravity, ADS space, or GKP mitten like GKP mitten or BDHM like a dictionary of the ADS-CFT. Just yeah. Actually, Of course, we need some assumption on the low energy spectrum, but it's actually natural. I mean, it's about the sparse spectrum and large N factorization. Large N factorization, this is a fact for the perturbation theory, so it's maybe this is not assumption. And third one is it's a complete universe of spectrum except symmetry, which means it's something like a universal representation or something like that. This is also very natural for the strong coupling large N CFT. So actually, assuming these, we can determine the large N gauge theory, spectrum of the large N gauge theory. Right? Okay. Of course, together with the conformal symmetry, assuming conformal symmetry. Okay. And okay, we just consider the field theory, and we can determine such spectrum. Okay. And large N factorization is of course proved the large N limit. In the large N limit, endpoint function is dominated by the 2-point function. Because here, 1-point function is 0 because of the CFT or something like that. Then 2-point function is dominated. So this is like using a weak theorem. So this means theory is a free theory. More precisely, it's a generalized free theory. Okay. Okay. So then because of large factorization, the low energy limit of the large CFT is a free theory, and then we can ask, what is this free theory? Okay. And of course, we know the answer now. It's a free theory on AD space. Yeah, including gauge, graviton, gauge field scalar. Yeah. Okay. But okay. But here, I want to stress that this determination of the Lorentz spectrum is not assuming that ADS CFT like things or D brains or something like that. Just some broad, I mean, natural assumption on the spectrum for the large limit of the conformal field theory. Okay. So this is something like a derivation of the ADS CFT in this region. Okay. Actually, here we consider free scalar, I mean, scalar field in ADS space. Then ADS space is like metric is this one, and here rho is radial direction, and rho equal pi over 2 is the boundary or asymptotic boundary of the ADS space. Okay, and then the equation of motion is Klein-Gordon equation, and we can expand scalar in ADS space with spherical harmonics and also time plane wave for time. And then for this wave function for rho is determined by the, of course, Klein-Gordon equation, and the normalizable solution for this is given by this one. So it's not important for my talk for the detail, but actually what I want to stress here is we can determine by the Gauss hypergeometric function, and energy, I mean, or spectrum of the theory is given by this one. And delta is, of course, a famous formula, but determined by mass and dimension of the space. Okay. And then, in summary, quantity field is like this one, and the spectrum is this one. So then the commutation relation Hamiltonian, this is a free field, so we can have this one, and then we can construct a focus space. That is this quantum field theory for this free theory. Okay. The point is this is same. This spectrum is same as scalar in CFTD. Okay. So this, yeah, the relation is established. And we can extend this to the graviton gauge field. I mean, graviton case, we need to consider the energy momentum tensor in CFT, but we can find this agreement between the same spectrum. So, okay. So we can establish these one. Low energy spectrum in CFT-D is the spectrum of free gravity theory on ADS space. So this is something like a derivation ADS CFT, and if the spectrum, because the spectrum determines the theory itself in some sense. So from CFT, CFT field knows everything. So from CFT field, we can construct a bulk local fluid in ADS. It's a bulk reconstruction. And also, usually we assume GKP relation or BDHM relation first to consider the ADS CFT. But in this setting, the GKP relation or BDHM is some result from this equivalence. Okay. And bulk reconstruction formula is explicitly given by these. Okay. Here, phi plus is a positive frequency part, or positive frequency or positive energy part. And P is a derivative. So this P is a derivative, and this O delta is a CFT primary operator. And this should be equivalent to HKL. HKL just assumes the BDHM relation is a dictionary of the ADS-CFT and use the same expansion. So this should be equivalent to HKL, and we can show its equivalence for some case. Okay. So this is the alternative formula for the bulk reconstruction. Okay, and now we give a from this we give a simple picture of bulk reconstruction. Okay, so then we consider the bulk local operator at the center at t equals 0. Okay, and instead independently we can consider the CFT state created t equal minus pi over 2 here. Okay, here. So this one. And this is a CFT primary field integrated over the whole space. Okay, smeared over whole space. So it's a spherical symmetric state. And of course, we can consider time evolution of this field to the t equals 0. Okay, so that is this field. Okay, then we can show using the previous formula this one. Okay, so CFT state created at t equal minus pi over 2 is same as bulk local state at the center. Okay, so at t equals 0, this is identified. Okay, in the free theory limit or general free theory limit. Okay, more precisely for this is for delta equal d minus 1, and for other values of delta, we need a derivative correction. But anyway, it's essentially this one. It's can be shown. Okay, this means to construct bulk local operator bulk local state. Yeah, it's reconstructed from the t equal minus pi over 2 CFT state. It's related by the light rays to the center. Only the such a state is needed. Okay, so this is very simple. And maybe you might think this contradicts with HKL reconstruction formula, but actually HKL reconstruction formula has many ambiguities, so we can represent it in many ways. And for some cases, we can show HKL reconstruction also gives this picture because HKL reconstruction formula is given by this one. So this is integration over this region with smearing function with some function. It's called smearing function. This one. But actually, this smearing function is divergent at t equal minus pi over 2 and t equal pi over 2. Then this integration is dominated by these points, these regions only. It's localized on this one. And this equation is not precise, but we can say a precise. Actually, from the HK reconstruction, we can show this is actually equal for at least for the delta equal d minus 1 case. Okay, so this HK my result doesn't contradict with HKL. So this is yeah. So what we have is a very simple picture. Yeah, yes, this operator can be constructed from this one or this one plus this. For the state, we just need this one, and for the operator case, sometimes we need this one. But anyway, okay, and we can argue that this localization should be occur by the causality, but I skip this one. And then I will move to the to consider the wave packet moving in a particular direction. Okay. Of course, bulk local state is something here is something not. I mean, is uniform or something like it's a spherical symmetric one. But we may think this is something like a constructed light rays here, so we can decompose it to these light rays. And maybe we can think this operator can be decomposed over the sum of these wave packets. Okay? And we can show, actually this is true. I mean, now we consider the not CFT field not over the whole space, but just a small region. A, we call it A, and consider the time evolution of this one to the. Then we can show using a formula. Using a formula, this state is like a wave packet moving in a light-like direction here. Okay, we can show using a formula this state evolving the time. I mean global time. It's represented by in a bulk. It's represented by the wave packet moving in these. And if you consider the here and integration over here CFT field, then it represents the wave packet here or something like that. Then if you consider the whole space, then it represents the bulk user bulk local field or bulk local state here. Okay, so this is also very natural. Okay, and it's then we can think this, yeah, in a bulk picture, this represents the wave packet here or here. But in the CFT picture, of course, there is no bulk. So what's in the CFT picture? CFT picture is like a massless or something like that. Also, this is very high energy state because it's very localized. Then it's evolved like light phase. Okay. Then this bulk local state, sorry, the wave packet localized in the center is reconstructed by the CFT state localized on this and this. So it's something like an entangled state in CFT. So this state, I mean bulk, I mean state is some entangled state. Okay. And of course here, if it's the bulk, sorry, if bulk wave packet is near here, then CFT state is also near here. Okay. This is called it's called BDHM relation. BDHM relation means it says a bulk field near the boundary can be identified as a primary field in CFT. Okay. So then our picture is very simple. Actually, here we can identify this in a bulk picture. Wave packet localized near the boundary is represented by the CFT near here, CFT primary field near here. Then its time evolution is like here because it's a wave packet of very high energy mode. And then CFT picture, it's also just time evolved. Okay. Okay. Then this field, CFT field, constructed from the CFT primary field by the time evolution is identified as a bulk local. But of course, we can consider not bulk local, bulk wave packet going to the center, but any direction. There are three-way packets here. But any of them is represented by the some different entangled states, locals near here and here. Okay. And we also consider some causality and duality, but it's also actually this picture is only consistent with causality in bulk and CFT, but I skipped this one. And finally, I will consider the CFT state supported in a region in our picture. Let's consider state corresponding to CFT state supported in interval A at t equals 0. Then we represent the CFT operator as the CFT primary operator integrated over the space-time. Okay, so here we just consider primary field without derivative, but if we integrate over the whole field, we can represent any operator. Okay, so then we consider such thing. And then CFT operator, CFT state supported on the region A is constructed from the operator here by the time evolution. Okay, its time evolution is it's called it's of course this region this region by the right cone is inside the region A. But if we consider this state and the time evolution of this one, then it's outside region A. So this is not supported. So CFT state supported in region A can be constructed from the state operator inside these regions. Okay. It's called cause diamond in CFT. And then this considers the state here. Okay. And then it's in the CFT picture. It's okay, like this one. It's time evolution is like this one. So it's within a causal diamond. And in the bulk picture, we can consider any wave packet. Any direction. Okay. And if we consider if we consider all states here and consider all direction here, then what we can reach is this within this blue line. Okay, so it's called it's the same as so-called causal wedge of A on t equals 0. Okay. So this means, P supported in the region A are given by the bulk state supported in the causal wedge of A. Okay, so it's called utah-tiny surface in this case. And we can recover it from our picture. Well, maybe it's not surprising, but let us consider the disconnected region. Okay, disconnected region A and B. A and B. Okay. And then, in this case, people think the so-called entanglement wedge. In this case, entanglement wedge is this inside of these region. Okay, this region is entanglement wedge. And people think the state inside the entanglement wedge can be reconstructed from the A and B. But it's a bit mysterious how to construct such a state in the wedge. But okay, it's something mysterious. But in a picture, this state considered here, it's represented by this one. So in a CFT picture, it is supported on this region A and B. Sorry, A or B, A plus B or something like that. Okay. Then we can consider from here any bulk packet starting from here. Okay. Anyway. So then, what we can reach by such a wave packet is this inside this blue line. Okay. So this blue line is also same as the entanglement wedge. Okay, so we here we express the state in entanglement wedge, the bulk state in entanglement wedge by the CFT state explicitly. Okay, so it's very interesting, I think. But maybe okay, I will skip this. And we can generalize this picture to the asymptotic ADS case also. If we assume the BDHM relation, then we can extend this one. And actually, in this case, CFT picture, it's asymptotic ADS case, it's not a vacuum, but some medium, I mean, some state. So in a CFT, it's, I mean, light of speed is not, I mean, not light speed. Sorry, light can okay cannot cannot go like with light speed. Okay, it's a time delay. So then in the bulk picture, it's we can consider the nu our light rays or light like wave packet, and it corresponds to some time like uh, time like wave packet, time like trajectory in CFT. And this is consistent with the Gao-1 it means CFT picture is, I mean, okay, I will skip this. But finally, we can consider the heavy star or something like that. Then there is a time delay. So for black hole, there is infinite time delay. And this means, I think, means it's black hole. I mean, user black hole. Not eternal black hole, but the user black hole formed by the user of stars or something like that. It's doesn't have insight. It's like a black ball or fuzzball or fireball, I think. But anyway, so this is the conclusion. The first spectrum gradient shift is identical to the spectrum free gravitational in ADS. And the bulk reconstruction ADS is rather simple and has an intuitive picture. And we also reconstruct wave packet in bulk theory from CFT primary operator. And our picture of bulk reconstruction can be applied to asymptotic ADS spacetime also. And there are many future directions, but I will skip here. So thank you very much for listening.